Chapter 5, Section 9. This is the last section of Chapter 5 that we're going to cover. There is one other section on hyperbolic trig functions and their inverses, Section 5.10, but that's not part of the AP, so we're going to go ahead and skip past that. So this is the last section in Chapter 5. It's kind of a long chapter, as you will attest to by now, but a very important section all the same. The type of integration that we will learn here in Section 5.9 is going to most certainly be seen on the AP test, as well as, of course, your assignment and your chapter test. So let's get started. Now, I mentioned a couple times in the previous video on Section 5.8 about how there were 6 trig functions, and that they're the derivatives of the not only the trig functions but of the inverse trig functions are paired up as opposites. I think I just listed it as the trig functions, but also the inverse trig functions. So I want to use that to come up with only 3 integration formulas. We don't need all 6 of them because of the fact that they're just opposites, and as I mentioned before, you just adjust a negative. So the theorem's integrals involving inverse trig functions: let u be a differentiable function of x, and let a be greater than 0. Okay, because we'd like to think of it in that terms. We don't have to worry about an opposite sign and changing, our quadrants and stuff like that. So we say that the integral of du all over the square root of a squared minus u squared is equal to the arc sine of u over a plus c. Now you may remember that the derivative with respect to x of the arc sine of u was equal to u prime all over the square root of 1 minus u squared. So we're reversing this, but notice that there's a 1 here, however there's an a here. So you can see the adjustment that has to be made. It is not a difficult integration finagle that you'd have to do. We're not going to bother with it, but I do want to bring to the point that for the arc sine, the a value, and a might be 1, so that would be a 1 there, but the a value appears only once, whereas with the other two, you'll see that the a value appears 2 times. So the integral of du all over a squared plus u squared is equal to 1 over a, the arctangent of u over a plus c. All these integration formulas to memorize. And the integral of du all over u times the square root of u squared minus a squared is equal to 1 over a, the arcsecant of the absolute value of u. You may remember that the derivative involved an absolute value for arcsecant. The absolute value of u all over a plus a constant. So what I'm going to do is just jump right into some examples, because there's all different ways you can twist these problems around, and including just adjusting the constant and such. You may have to complete the square, all sorts of things that we can have fun with. But first things first, this should look pretty much just like the formula there for the arc sine. Your a is 3. You don't have to write this down, but when you're first starting out, it's probably best. Your u is x, and your du is dx. It is all set up. You have everything that you need right here, so this is equal to, no adjustment to be made here, this is equal to the arc sine of u over a, x over 3, plus a constant. Done. Nice. This one is the one without the radical in the bottom, so you have to pretty much be thinking arctangent here, because that's the one without the radical. The other two have them. And so in this case, a is the square root of 3, and u would be 2x, because it has to be u squared, so it would be 2x times 2x. That means that your du would be 2 dx. Got to make an adjustment here. Let me grab my red pencil. I need a 2, so I'll put a 2 here and a 1/2 here, and I'm ready to roll. This is equal to 1/2 times. Now it's going to start out as 1 over a. So since a is the square root of 3, I have 1 over the square root of 3. Then the arctan of u over a. Now the u is 2x over a, which is the square root of 3. All that plus c. Now I know it seems almost like a contradiction, but I don't think I'd leave the radical in the denominator here, but I probably would here. Okay, I doubt if they're going to, on the AP, if they're going to make any adjustment in here. But this is 1 over the 2 square roots of 3, and if I multiply top and bottom by the square root of 3, I get the square root of 3 all over 6. It's a constant. So I want to go ahead and simplify that a little bit. But this has got the variable mixed in, so I'm going to leave him the same. Nope, one too many jumps there, and this would be 2x all over the square root of 3 plus c. All right, there's my guy. Now the next one doesn't look like an arc sine, or let me just bring it down a little bit so you can see it. Doesn't look like an arc sine or an arc tangent. First off, there's a radical, so it doesn't appear to be an arc tangent, and it kind of looks like it should be an arc sine because it just has the radical expression, except that notice it's a squared minus u squared. U is your differentiable function of x. This is u squared minus a squared. So you say, well, something surely amiss here. It kind of looks like this one here with the u squared minus a squared, but there's an extra factor here of u. Well, if I make this guy my u squared, that means u is e to the x. That means du would be e to the x dx. What if I was to take this guy, multiply top and bottom by e to the x? Doesn't this look exactly like the formula here? Now, let's see if I have that. Yeah, I think you can see that. The formula here for the arc secant, because I have my du up top, I have my u, and I have my square root of u squared minus a squared. A in this case is 1, which is always convenient. So this is equal to 1 over a, which would be 1 over 1, which is just 1. I don't need to put a 1 down. The arc secant of the absolute value of u all over a, which you get a is 1. So I have the absolute value of u, which is e to the x. Now the absolute value of e to the x is just e to the x because it's always positive. So I wouldn't put down the absolute value of e to the x. I mean, you could, but you would want to take an extra step here to go ahead and rewrite this in simplified form here. E to the x, put that in parentheses, plus c. And there's my guy. You had to do a little bit more than a constant on this guy. You had to c to multiply e to the x. You say, well, I don't think I would be able to know how to do that, or well, that's where the practice comes into play. You'll get some practice on these. All right, now this guy here probably looks a little bit more like the arc secant. If you were looking, oh, I don't even know if you were able to see that last part there. I might have had that too low. The arc secant here up at the top, all right, it looks like in this case that a is 2 and that my u would be 3x, which means that my du would be 3 dx. Now, very conveniently, as you can see here, I need a 3 in the numerator for my du, but I need a 3 in my denominator as well for the u, because it has to fit that form. There has to be that factor of u. So this, I don't even have to pop anything out in front. This is exactly what I want. So this starts out as 1 over a. That'd be 1/2 the, oops, if I can write, the arc, can you see this? Yeah, you should be able to see this. The arc secant of the absolute value of u, which would be the absolute value of 3x, all over a, which is 2, plus a constant. And there's my guy. Not so bad. They can get a little messier, as you're going to see here in some of these next examples, but those are pretty straightforward. You did have to adjust on a couple of them there. All right, let's move this over to the side. And now we're cooking. All right. Now this guy here looks like trouble because there's a factor, there's a term that contains the variable x in the numerator. So what you have to do in this case, you say, well, this is not going to fit the arc, because it kind of looks like an arc sine here, a squared minus u squared, where a is 3 and u would be x, but it doesn't fit that because that's not du. I've got a factor of x there. I mean, if it was just a 3, I could pop it out in front. But what if we were to take the time to rewrite this as x dx over the square root of 9 minus x squared plus 3 dx all over the square root of 9 minus x squared, and use the fact that the integral of a sum is the sum of the integrals. So by writing it, notice common denominator, by writing it in this form, I can do one more kind of interesting step here. I'll write this one as 9 minus x squared to the negative 1/2, right? Then I have x dx. And then this one here, I'll just pop the 3 out in front. The reason I'm doing that is this is going to be an arc sine, But this guy here, this is going to be a u to the n, and I just have to set up my du. Because if my u, this is for this one here, up there, if my u is 9 minus x squared, my du would be negative 2x dx. So I need here a negative 2, I'll put it out in front here in red, hopefully you can see that okay, and a negative 1/2 to balance that, and I am ready to roll. So this guy integrates as a u to the n du, my du is set up, so up to a half over half, well that's going to cancel the half here, not the negative, but it's going to be up to a half, so that's going to be negative the square root, because it's going to be to the half power, of 9 minus x squared. Now this guy, he's ready to go too. This is going to be an inverse sine, so that's going to be plus 3, that's this 3 right here, the arc sine of u over a, so that's going to be x over 3, I'll put it in parentheses, plus a constant. And I don't think that's going to neaten up any more than what I have right here. That's a good looking problem. Notice the trick there. Here's another one with a trick. It looks a little bit with that x squared plus a squared here in the denominator, like, and there's no radical, it may be an arctan, but it's not that easy because my numerator isn't set up for that. And my numerator would have to be at best just a constant, and I have an x to the third here. So before I go any further, when I have a rational and the degree of the numerator is greater than or equal to the degree of the denominator, I'm going to divide. So I'm going to divide here. Hopefully you can see this. My handwriting is just so bad at times. And x to the third plus 0x to the second plus 0x minus 2. What times x squared gives me 3x to the third? That'd be 3x. Now multiply 3x to the third plus 0x squared plus 12x. Subtract. When you subtract, it's the same as adding the opposite, so I just change the signs. Add straight down, I get a negative 12x minus 2. Now, that's going to be my remainder because x squared is not, it has higher degree than that. So this means that this is equal to the integral of 3x. All right, I have a minus in both terms here. Watch what I'm going to do here. I'm going to go ahead and write this as minus, and then I'm going to write 12x plus 2 all over my x squared plus 4. So all I did was rewrite this by dividing, and I was, a little sneaky there with my negative because I had a negative in both. So I am going to now break this into 3, count them 1, 2, 3 integrals, kind of along the same way that I did in the previous example, because I have these two terms in this numerator. So I'm going to write this as the integral of 3x dx. All right, careful now, minus all of this, the integral of 12x dx over x squared plus 4 plus the integral of 2 over dx over x squared plus 4. Now I did that to emphasize the fact you have to be very careful with your signs here because I'm subtracting all of that. So I'll break this apart here, and this guy's ready. This guy's not too far off. I'm going to do a du over u here. This guy is going to definitely be an arctan. So I'm going to take one extra step, drop those parentheses, set up my my constants here. So I can see if I can do this in the space that I have here. Minus the integral. Now, what I have here is an x squared plus 4 in the bottom. So if this is my u, my du would be 2x dx, and I have 12x dx. So I'm going to break the 12 to 6 times 2. Put the 6 out in front. Let me go ahead and put the 6 out in front, and then write this as 2x dx over x squared plus 4. Now he's ready to go. And then I'm just going to pop the 2 out in front. So this is going to be minus 2, the integral of dx all over x squared plus 4. And all 3 of these integrals are ready to go. So up to 2 over 2, that would be 3 halves x squared. This is going to be a du. And notice that my u here, du over u, my u is x squared plus 4. It's always non-negative. So I'm going to write minus 6, the natural log of the quantity, not the absolute value, because it's always positive. And then here I'm going to write minus 2. Now notice here that my a squared is 4, so that means a is 2, so it starts out as 1 over a, so times 1/2. Now notice what happens here, right? The arc tangent of u over a, that'd be x over 2 plus a constant. Now, of course, we know that 2 times 1/2 is just 1, so I mean, I'm just going to erase it. You can still see it there, hopefully, but I just erase it because that's just a factor of 1, and that's as simple as it's going to get. I don't think I can simplify that expression any more than that. Now, in the next couple of examples here, there's no radical in the denominator, but it's not in the form a squared plus u squared or u squared plus a squared for an arc tan, because it's a trinomial. So what I'm going to do here is I'm going to see if I can complete the square. Watch this. Now I'm going to write this as x squared minus 4x, and then I'm going to put plus 8 out here. To complete the square right here, I would need a plus 4. So if I add 4, I better subtract 4 from the same expression for it to balance, and I get dx all over. Now this is a perfect square trinomial. This is x minus 2 quantity squared, and of course this is plus 4. Look at that guy. Can you see my u is x minus 2, my a is 2. This is all set up, and of course my du is dx. It's there. So this is equal to 1 over a, so 1/2 the arc tan of u over a, which would be x minus 2 over 2, the quantity x minus 2 over 2 plus constant. Boom. That's the guy. I'm going to do something very similar here, but notice that all of my terms in the denominator have a constant factor of 2, so I'm going to just factor the 2 out and bring it out in front as 1/2 the integral of dx all over x squared minus 8x plus 10. All right, so here we go again. Now I'm going to get this one hopefully set up so that I can rewrite this. Now to do this one, I hope I have this written down right. All of a sudden, kind of half in my head, I'm wondering if I'm going to get this to work nicely here. So this is x squared minus 8x, so I would need a plus 16 here. Did I write something down wrong here? Because I only have a plus 10. So if I have the plus 10 and I add 16, I got to subtract 16. That's going to give me a negative. I'm not liking this one bit. Maybe I wrote the problem down wrong, or maybe I'm losing my mind here. X minus 4 quantity squared minus 6. I can't have that minus 6. So let me just double check to see if I had written this down wrong, because I'm pretty sure I took this one out of my notes. And it doesn't look like I did here. Well, I can't integrate this because I can't complete the square. Is it supposed to be? Oh, heavens and Murgatroyd. Help me out here, people. When you see me do something silly, start hollering at me even though I'm not around. I factored the 2 out, but I didn't factor it out of these two terms. Heavens to Murgatroyd. This would be 4x and a plus 5. And then this would be, oh, heavens. This would be a 4x. This would be a plus 5. I would need a plus 4 here, so I need a minus 4 here. Oof. Heavens, the Betsy's here. So, I need the 1/2 though. And this is going to be x minus 2 quantity squared, and that's going to be a plus 1. Whew. Now I can use the arctan because my u is x minus 2, my du would be dx, and my a would be 1. Oof. This is 1 over a, so that's going to be 1 over 1 times that half out in front, the arctan of u over a, which would just be x minus 2 plus a constant. Whew. I wish I could say that I did that on purpose just to make sure that you don't make that same mistake, but I just messed up. And I'm not going back and changing my video, so you'll get to enjoy this one again and again and again. All right, one more guy up here. I put him in there even though it involves completing the square, but notice the negative in front of the x squared, and also notice the radical. So more than likely, if this is going to work, it's going to probably be an arc sine, because it's certainly not a du over u or a u to the n du. So what I'm going to do here is I'm going to just do a little bit of scratch work. I'm going to take 3 minus x squared. I'm going to write it as the opposite of x squared plus 3x. Then I'm going to factor a negative 1 out. And that's going to give me x squared minus 3x. Now, the reason I'm doing that is because now this kind of fits the form for completing the square. So I would need half of this and then square it. So that would be negative 3 halves squared positive 9 fourths. But I didn't really add a 9 fourths. I subtracted a 9 fourths here because of the minus sign out in front. So I'm going to have to add a 9 fourths to it to keep it equal. Can you all see that? I hope. So now I'm going to pop him out in front. I'm going to write 9 fourths minus the quantity x minus 3 halves quantity squared. And by rewriting this into this, I fit the form, or at least a lot more closely, to an arctan. This is the square root of 9 fourths minus the quantity x minus 3 halves quantity squared. So in this case, my u would be x minus 3 halves, so that means my du is dx, that's nice. And my a would be 3 halves, the square root of 9 fourths. So this is 3 halves. So this is the arc sine, so there's no 1 over a out in front. This is just going to be the arc sine of u, which is x minus 3 halves, all over a, which is 3 halves, plus c. Now, I don't think I would leave it in this form. I would probably multiply top and bottom by 2 and write this as the arc sine of 2x minus 3 all over 3. That looks so much nicer. Okay, there's my answer. So be careful with your algebra there, especially with that negative in front of the x squared. Students sometimes have trouble when they're completing the square when that happens. Now, all the basic integration rules are on page 391. A little bit ago I was mentioning how the basic differentiation rules were on one of the other pages there. I don't remember which one now because I put my papers off to the side, although they're not so far away. They were on 385. 6 pages later, these are your basic integration rules. And these also need to be put to memory. Oh yes, oh yes, oh yes, because there's so many problems that are similar looking. If you don't know your rules, you're going to have trouble. And with differentiation, you can differentiate just about anything. But with integration, they have to be set up. Now look at these 3 examples. It says, consider the following 3 integrals and how similar they are. 2 of them integrate. Which one does not? Well, you look at it, look, you see, well, they're so close. Here I have an x in the bottom, here I have an x on top, here I don't have an x. Well, this guy here, that's an arc secant. You see the form u squared minus a squared, and I have the u and the du right there. This guy over here, he's not an inverse trig one. He is going to be x squared 4 to the negative 1/2 x dx. This is going to be a u to the n du, and I just have to finagle the constant. This guy doesn't integrate. They're so similar looking, you have to be very careful and you have to know your integration rules. All right, one more time. What about these 3? 2 integrate. Now, none of these are going to involve an inverse trig function because you can kind of see the format of them. But like I said, one of these things is not like the other. One of them does not integrate. So you look at this and you say, well, I don't know. Yep, you sure do. If I brought this x up top, that would be 1 over x dx over the natural log of x, and this is a du over u. That would be my u. The derivative of natural log of x is 1 over x dx. There's my du over u. Integrates. This guy, this can be thought of as the natural log of x. See the x in the bottom? Times 1 over x dx. If I have him to the first power, this is a u to the n, and there's my du. This guy does not integrate. Now, you might be able to integrate this one with parts, but it's been so long, and it's not part of the AP, so we won't worry about it for right now, but this is the guy that doesn't work. These 2 do. So you have to practice those problems. You're going to need to know how to do integration, and you need to make sure that you have all the rules down in your memory. And as always, practice, practice, practice.